speaker of the day, and I am extremely happy to introduce him to you all. The first speaker
Madam,
is...
please be brief. No need to introduce too long because we are already running late. Yeah.
Sir, it is very difficult to brief out your CV, but I'll try my level best, sir. So let me do the work. Okay, thank you. All right. So in brief, like, he is a professor in Department of Chemistry, IIT-Madras, and he did PhD in 2004. Then he worked there as research fellow in University of Coimbra, Portugal in 2005. Then postdoctoral research fellow from University of Aveiro, and then research associate from Queen's University, UK. Now, to go into the like, this was the academic qualification, and he has many awards to his credit. The major achievement he has, that he has a model named after it, which is Gardas and Cutino model. And awards and recognitions, he has recently received Institute Research and Development Award. Then he received High Impact Author in 2019 and rated as top 40 high impact author by American Chemical Society Journal. Then he was recognized among 25 emerging investigators from American Chemical Society in 2018, received Publon's Peer Review Award in 2018 and 19, and was placed in top 1% of the reviewers in chemistry on Publons. He has received Institute Research and Development Award in 2015, to name a few, Professor H.C. Gore Memorial Lecture Award, Dr. Arvind Kumar Memorial Award, Young Scientist Award, Best Young Researcher Award, Professor Oswald Young Scientist Award, Sri J.C. Bose Patent Award, and lot many. He has delivered more than 135 invited talks, and is reviewer of more than 50 scientific journals, more than around 6,000 citations, etc. So I think I cannot do justice while reading your profile. So I think I should now welcome you to take the dais and just start sharing your expertise with us. Thank you so much, sir. Now you can start.
Thank you, madam. Thank you very much. Sorry, I was a bit rushing because I have another meeting at 11. So it's fine. Yeah. So good morning to one and all. I'm happy to see that more than 250 participants are there, and I am more than happy to see the CH students of 17 batch, 18 batch, 19 batch. So it was nice that they have joined with the roll number. So I'm very happy to see that. So nice of you. I would like to thank, first of all, entire Nirma family and Institute of Technology particularly, and the director, sir, Professor Rajesh N. Patel, and the head of the Department of the Chemical Engineering, Professor Sanjay S. Patel, sir, and the convener and co-convener of this national webinar, Dr. Neha and Dr. Amita. Thank you all. And apart from this, I have many friends in Nirma, not only in chemical engineering, but across the department. So I have very good association with Nirma and Gujarat, because I brought up in Gujarat, studied in Gujarat. So we have a lot of affection. So any invitation from Gujarat, I never turn down. So I will try my best to accommodate. So having said that, let's go into the detail. As Professor Rajesh Patel sir told, the future is collaboration. I'm going to press more on two things. One, you could have seen that 16 colors logo, 17 colors logo, I put the round logo. I'm sure many of you may be knowing. If you are not knowing, you will come to know today what is that logo is. That is the future. That is the future. So I put right hand side, taking care by three hands. These three hands are nothing but academia, industry, and the sustainability or the government. So you can see that how collaborations are crucial, and how sustainability is crucial, and understanding and mutual respect is crucial. That's what I'm going to emphasize, because I heard that so many youngsters are there. And to give a justice to the title of the webinar, I'm going to talk something about the importance of the analytical techniques. And to give a justice of the title of my talk, I'm going to talk about the thermophysical properties importance. So it's a mix of many things. And though I'm from chemistry department, I'm not going to the depth of the lot of chemistry to bombard you, but I will certainly try to convince you that the chemistry is essential part of the chemical engineering, and both together can do wonder in application sites. So without much delay, let's begin the show with the thanks to the entire Nirmal family. And I would like to start with the blessings of the goddess of knowledge and the goddess of the health. Both knowledge and wealth are essential for a sustainable research. And for a research, this was I was talking, you no need to count, these are 17. And this is the logo of United Nations Sustainable Development. This is the future now. All countries are coming together. Any international proposal you are asking or any ranking is coming for the institute level or the international level, they are addressing in terms of which number of sustainable goal you are focusing. Of course, India is doing much well in clean water and sanitization, that is a 6, and clean, affordable clean energy 7, apart from many other things, climate action and so on. So today's my talk is also going to touch on a few of these things, especially the industrial and sustainable communities and all these things, 9 and 11, or some more things. But let's not go into the detail. I only my intention to put this slide is the young students at least should know that there is a lot of talk going across the world about the sustainability, and this is more of especially in this kind of pandemic situation. So if you don't save the nature, nature will get back to you. And as I told you, 3 hands are very crucial in the sustainable development and the cross and this collaboration. There is no development will go to the national, international, and the industrial level without creative innovation by joining hand in hand by 3 sectors. But that is academia, industry, and the government. All 3 are very crucial. And industry can come up with the corporate social responsibility or can come up with their funds to the academic institutes, and government can help the both small scale industries and academia. And academia particularly, we need a support from the directors and the vice chancellors and the deans and the head of the department, especially when the colleague or faculty join in the young stage, they have a lot of enthusiasm and energy to do. So if you want to give him more and more facilities after 10-15 years, by that time he might be engaged in other things, or his priorities might change. So all these things are very crucial. I'm sure the India scenario is changing very fast. Now we are the 3rd largest country in the world in the publications, and not only in the publications, our ranking in the innovations and patent is shooting up. But I would like to see, as the current government is saying, make in India and what do you call, everything is indigenous. So that stage should come. Now we have done enough academic research, enough industrial talks, enough patents. Now we need to join hand in hand. All 3 should go together to convert into products. And as a humans or as a citizens of India, we should encourage that. So having said this, let's go into the further detail. The development will sustain only the researcher, academia, and the government, all 3 things in point of societal need, economic need, and the environment. So once the development combined with the society, economy, and the environment, that development only sustain. So in the earlier slide, I said academia, industry, and government. This slide, I am saying societal need, economical need, and the environment. So the trio of double trio or triple trio, I will tell one more trio. These are the key for the sustainability. And if you protect nature, then only nature will. No doubt we need industrialization. No doubt we need to progress. We need more and more product. Today we are seeing smartphone, everything. I'm sure many of you, out of these 250 people, might be attending this talk on mobile. And seamlessly they are seeing with a big screen and a good quality of pictures and everything. So this development is essential. And now our biggest challenge is long battery life. We are running so many things at a time, and that time you will come to the chemistry people or chemical engineer and also. And as said, I'm in line with Professor Rajesh and Patel, what he said, everything is a collaboration in future. Science you know much depth of science, but you don't convert into product, and you don't know the engineering part of that product converted from the based on this science, it is like a dream. And you know very much engineering, and you know designing, and you know process and product, everything, but you don't understand the molecular interaction level, whatever the chemicals are involved, their characterization and their composition, then it is like a simply calculating. So we need a good scientist, we need a good engineers, and we need a good policy makers, we need a good government, and then only the developments can be sustained. So future is collaboration. We need all kind of people. You see, the petrochemical based solvent market is growing annually by 4%. And this is mainly due to the automotive and the construction industry and the energy sector. And the construction in the last decade in India boomed exponentially. In largest growing metropolitan cities across the globe are more than 50% in the top 50 are from India. And that's a high-rise buildings and everything. And once you go for an automotive industry and the construction industry and the energy industry, these are the three big industry in the last decade consuming so many petrochemical based solvents. And you see, it's about $57 billion market. And most of them having a lot of problems and environmental problems. And due to this strict and stringent environmental regulations, now the scientists and the engineers are looking for alternative to this petrochemical based solvents like ethylene, dodecane, methanol, butadiene, xylene, toluene. And when you look for alternative, you go to close to the nature. Baby has any problem, will go to mother. Similarly, we have any problem, we'll go close to the nature. Close to the nature is always sustainable. Close to the nature is always environmental friendly. So we are looking for bioalcohols, biodiols, bioglycols, and we are going to talk new class of compounds, that is molten salts, new class, ionic liquids, and deep eutectic salts. This is one of the recent solvent in the market, and it's becoming very popular so quickly. The serine is a cellulose-based solvent. It is derivative of levoglucosylcellulose, and it is told that serine can replace dipolar aprotic solvents like N-methylpyrrolidine or DMF or so other things. The only problem is the cost, and this is the and if anybody is looking for any most environmental friendly solvents, they are going close to the nature and water and the cellulose derivatives and the bioalcohols. As Neha madam introduced me in the detail, I'm from the chemistry department. We have a very beautiful campus, and please drop me email if you are visiting Chennai. I will be happy to arrange the department and the institute visit. I hope my students will be back soon, and one of student will take you to the various departments. We have varieties of the birds, beautiful campus. It's a mix of nature and science. You just go in the morning, early morning walk, you listen varieties of the birds, and we have so many notorious monkeys and poisonous snakes, mongoose, and so many professors. I would like to thank all my students, collaborators, and funding agencies and the NIRMA institutes to giving this opportunity, because all the work what I am going to present done by my students, and due to the support of my collaborators and funding agency, the bold names the students have been graduated and left. They are faculties in the India various institutes, or they are postdocs abroad. I'm going to talk initially little bit about why we need to look for alternative to this organic solvents, and what we are doing in the last 10 years at IIT-Madras. What are the ionic liquids, where it stands in national level, why we need to focus on thermophysical properties, and how we can tune these thermophysical properties for a specific applications, and so on. I hope I can give justice to this talk in next half an hour or so. So in when I talk so much about sustainability, the thumb rule for any engineer or any scientist to look at how many of these 12 principles of green chemistry your research area is touching upon. Whatever I am going to present, we are going to focus at least out of this 12, the one prevention, the 12 principles of green chemistry, prevention of organic volatile solvents, three less hazardous chemicals. So compared to organic, ionic liquids or the deep reductive solvents are less hazardous, and the designing the safer chemicals and the safer solvents and auxiliaries. This is the main theme of my entire talk. So we are looking for a new solvents for various applications as a dissolvent, as a separating agent, as a catalyst, and so on. And one more is a renewable phase. We are looking for anything we can take from the nature. So these are the few points which I'm going to touch from the 12 principles of green chemistry. If you look at the 12 principles of green engineering, I'm not going to touch all 12, but mostly the two, that is prevention instead of treatment. 4, maximize the efficiency. 5, output pulled versus input pushed. And the 12, renewable rather than depleted. So when you choose any new research area, when you choose new research topic, when you go for industry, when you go for a next job, when you go for a postdoc, when you go for a PhD, when you go for any positions, look that whether you are interested in that position or not. Once you are interested, then you see whether this is a societal need or not, whether this will enhance the country's economy or not, whether it is sustainable or not. Today it is on the top. Will it be top after 10 years? Will it be top after 15 years? So, and is it focused on principles of green chemistry and principles of green engineering or not? This is the overview when you look for the new people or a new topic or a new job. So, as I told you, compared to the solid state chemistry or the solid state science and the gas phase science, the industry academia are dominated by the bulk phase or the solvent phase science. The solvents are the crucial in many process and product design and many applications compared to the solids and the gas. When I say solvents are crucial, they play a major role in many areas of technology. And that time, one more problem comes that these are the solvents which are the very large portion of volatile organic compounds. And due to their volatility, high vapor pressure, and low water solubility, they are the contributor for so many problems like ozone depletion, air pollution, global warming, climate change, and human health related problem, whatnot. So what to do? We cannot stop them using. So we have to look for less volatile or less toxic and renewable and the solvents with low vapor pressure or high boiling point or water solubility. This should not lead other problems. If somebody asks what is the ideal replacement, the solvent should have low volatility, high chemical stability, high potential to recycle, and should not lead to other complications. When I say sustainable, it depends on 3 R: reduce, reuse, and recycle. Our solvents is focused on that. Earlier solvents quantity can be reduced, that is first R. Can I reuse this several times? That is the second one. If after reusing several times, can I recycle and make it fresh again? This is the third R. So we need to think. But when you look for a new solvent, or we call environmentally benign solvent, more eco-friendly solvent, what are the challenges? The challenges are you need a varieties of the nature. You need a different polarity, different basicity, different protic nature or aprotic nature. When I look for purchasing a new mobile in Amazon or Flipkart and anywhere, what are our challenges? I want mobile screen should be big. I want battery life should high. I want what you call the RAM should be very high. I want the size should be what you call the GB more 128 GB. And having said all these things, and I say price should be low. There is nothing called cheap and best. We have to compromise somewhere. You want best features, you have to pay more. You want to pay less, then you have to compromise the feature. First, biggest problem in the battery industry, if you want high battery life, that means the battery's weight will increase, and that's in the mobile weight of 200 gram, most of the weight is due to the battery. Any smartphone bigger than 6.5 inch and long battery life, 500 or 5,000 or 6,000, you won't get less than 180 gram or 190 gram because the battery you can't make. So similarly, when you look for a green solvents here, you have a challenge of mix and match. Polarity, basicity, the complete plot, if you see the polarity versus basicity, the common non-polar, polar and polar aprotic and polar protic solvents I have listed here. These are the common solvents used in industry and in academia, and the spectrum is full. But if you look for environmental friendly, the spectrum is very wide. So it's our duty to fill this entire spectrum so we can have more and more choice. If I want to buy a new wallet or a new pan, instead of going to one brand shop, I will go to shopping mall. Why? Because I have so many varieties and so many shops at same place. So depending on my budget, depending on my choice of color, depending on my choice of brand, depending on of size, I can get. Chances are very high I get it in a shopping mall because you have so many shops. Similarly, when you provide more and more pool of solvents as a scientist and as an engineer you develop, then industry people can take care. Then they can look for replacement for this volatile organic compounds or the petrochemical based solvents. We can't simply just say like a politicians, industry are damaging environment. But you show the alternative to them. If they are not following, then you say. You show them and you show it's not easy to change any solvent or any process and establish the technique in any industry. That takes several years. Before coming back to IIT-Madras in 2010, I was in a Petronas Malaysian company-based project working in UK. That was in 2008 to 10 to reduce the tan of a petrochemical-based, what you call the crude oil. We were so successful, damn successful. We have successful in research and getting patents and getting publications, but still the industry is still unable to change because they have thousands of questions when they want to replace the well-established method. And it's not easy to convert any new laboratory technique into the industrial scale. It's not easy. You know, in the same with the vaccine or medicine, today all people across the globe are looking at the scientists for the vaccine development. This vaccine, whatever going to come now in the world, it will be the one of the fastest vaccine developed so far. So each thing takes its own time. Similarly, when you want to go to industry, you have to check several things. So I'm going to talk next 15-20 minutes on ionic liquids. This is like an old wine, new bottle. Why I say so? Because it's a class of a molten salt. Molten salt we all know. We know the sodium chloride. Me too. Not me too, but hoy swadma kharu. The salt, without which you cannot eat many things, and it's one of the most crucial ingredient in our kitchen. What temperature it melts? We know it melts around 800 degrees Celsius or above. So we are talking about the salts which are liquid at room temperature or nearby room temperature. And these are the new class of molten salts. They have potential to replace volatile organic compound due to their combination of unique properties like negligible vapor pressure, large liquidity range, negligible flammability, wide electrochemical window, high ionic capacity, conductivity, and above all, high solvating capacity and varieties of the structure possible. These are the hybrid salts. You see any common salts, both cation and anion are inorganic. Here we are talking about the hybrid salts where one of the ion is organic and another ion is inorganic. Usually the cations are heterocyclic compounds or tetraalkyl ammonium, tetraalkyl phosphonium, and the triazolium, imidazolium, pyrazolium. These are the heterocyclic compounds here, and the cation size is usually large. And the anions are very small. Smallest is halides, chloride, bromide, iodide, or tetrafluoroborate, hexafluorophosphate, triflate, bistriflamide, nitrate, and dicyanamide. It's very small compounds compared to the large cation. And based on this, that's why I said it's a hybrid. Hybrid in the sense one part is organic and other part is inorganic. And having said cation and anions are large pool is available, the third component is alkyl chain length. You can attach to the cation or sometimes to the anion as well. Methyl, ethyl, propyl, butyl, hexyl, heptyl, octyl, nonyl, decyl. Big chain. So, based on cation and anion and the alkyl chain length attached to it, the millions of ionic liquid on theoretical acid. On paper, millions of ionic liquid. If you ask, in reality, millions are possible, I will answer in the stage. And as I told you, the sodium chloride can melt above 800 degrees Celsius, but these are the salts which are liquid at around room temperature. Because of their asymmetry in the size of the ions, they cannot come closer together. They do have interaction, so they are coming close, but they can't pack together because of uneven size. And because of this, they leave a lot of void volume, and because of this, they are in liquid state, neither gas nor solid. And if I take a glass of water and then add sodium chloride into it and stir it, can I say it's ionic liquid? The answer is no, because there is ionic solution where Na plus ions and Cl minus ions are hydrated, surrounded by H3O plus and OH minus ions. But in case of ionic liquids, the ions are surrounded by its own ions. The cation of ionic liquid is surrounded by an ion of ionic liquid, and vice versa. And due to this, they possess a combination of unique properties. And they are multitasking. If hero is good, we will watch movie. And if the same hero can do comedy also well, we will be Sone Pe Suhaga. He does comedy also well, he fights well, he delivers dialogues well, his expression is well. What else you need? So these are multifunctional. Ionic liquids are not a single function, they are multifunctional. When they are used as a catalyst or the solvent, on top of that, they will do another thing. It's like a buy one, get one free. As I told you, Sone Pe Suhaga. So it's a multifunctional, and it's very attractive, and so many unique things and so many good things. Having said all these things, every coin has a second side also. If you ask me, sir, so much you told good about this, can you tell some challenges where it need to be addressed? The biggest challenge with this field or ionic liquid is viscosity. Once viscosity is high, you have several problems whenever you have uniform stirring, mixing, pumping, heat dissipation, and transport involved. So all these places, the cost is all these places wherever you need uniform mixing, pumping, transporting, heat dissipation, transporting, the cost will go high, and sometimes it will also challenging to go to the application. The second one is a cost. Compared to the organic solvents, the cost is high. Of course, these both problems can be addressed same time, like ek tir do nishan. I will tell you. So instead of using them in the pure state, look for the mixture with some other organic solvent or water. Then you may ask questions, sir. One side you said replace organic solvent, and again you are telling use organic solvent. As I told you, any industry, completely new replacement and convincing, it takes decades. So in the existing one, you add something as addition. So it would be perfect. I request all students, please mute mine. This is one way. Your turn will come after mine. So what to do? Use the existing one and add ionic liquid as an additive or a small quantity. So it will have dual or triple advantage. One advantage, viscosity will reduce drastically. Second advantage, cost will reduce drastically. And the third advantage is amount of the organic liquid required will reduce drastically. Anyway, you have to see that about 2 decades ago, when this research started, Most people who are concentrating on electrolytes, solvents, extractant, catalysts, lubricants, or energy, heat transfer fluids, fuel cells, solar cells, so on. Today it has touched up all fields, biomass processing, because of these unique properties. If you look in the SciFinder, it will showing you more than 86,000 papers in last 2 decades, and more than 17,000 patents, more than 50 books, all in SciFinder. So every year this is touching upon close to 6,000 publications. And if you look in another website, that is a SciFinder, and now it is a Scopus, more or less same. Some number will not match because the the sources are different, and some conference papers, some open access journal, and some patents. Here patents are not included. There it was included. So you see the field is ever growing. The first paper or the first review in this field written by Tom Welton, who is currently the president of Royal Society of the Chemistry, his first review paper has been cited more than 11,300 times in last 20 years. Can you imagine a single paper crossing 11,000 citations just in 20 years? That shows the popularity of this field. I have highlighted two names. Professor Joan Putin from University of Portugal. Professor Chris Herdecker was in Queen's University Belfast. Now he is in Manchester. So I had opportunity to work with both of them during my postdoc during 2005 to 2010. Let's go where India stands. India, as of now, it is in the fourth stage in this field. But by the end of this year or by the early next year, it is going to be a third. More than 150 affiliations, including Nirma University, are included in this unit. More than 150, that's a huge number. That's a huge number of affiliations in a same country working on a same topic. Why so? It's not only chemistry and chemical engineering. It's material science, physics, other parts of engineering, biochemistry, molecular biology, energy, environmental, pharmacy. So many fields it touched. What could be the reason? Solvent. I told in the beginning, the solvent phase research is dominated in academia and industry. So wherever solvents have been used, people are looking for alternative. And it's not only on the paper. It's a German-based Ionic company. You see the R&D scale, pilot scale, and the commercial scales, the applications of this ionic liquid. And this is another company, German-based BASF, and this is a list. I have extensive list at the end of my talk. I will show you that. How many companies across the globe have took this ionic liquid in the form as a solvent, as an extractant, as a catalyst, as a performance additive, and gone to R&D scale, to pilot scale, to the commercial scale. So the no doubt, by publication and patent side is good, by application side it's good, and all this happened in 2 decades and ever growing. So what is the challenge now? Out of that 80,000 papers, if you look at, most of them are focusing on the applications, whether working or not, or the properties measured, new molecules synthesized and done. What was missing? Somebody stopped sharing mine. Am I audible, madam?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Yeah, I'm sharing again. Is it visible, my slide now?
Yes, sir. Yes, sir.
Yeah. So, what we are focusing at, while much devotion is given to the application, but least understood is their structure property correlation. Why particular ionic liquid behaving so, and what is the chemistry behind, why they are so great, and how it is helping. This was lagging behind. So this is one of the paper I like very much. It's very quite old paper, but still it is this is about a decade ago paper. But how the industrial requirement of studying the properties and how academic requirement is different. This I will emphasize little bit, and then remaining slides I will skip if time doesn't permit, because this is what I want to talk to all the students of this Nirma University and across the India who are attending, that please remember, when you do any project or any research in the laboratory, You don't think that only this is for a degree, only this is for a marks, or only this. I'm sure you will be happy. Your research will click and go to the next level. If you would like to so, you have to be very serious in noting down your observation as it is appear. Please remember, science is not about showing the perfect results. Your results have to be a perfect and come all points in one line, and regression coefficient R square is equal to 0.9999. We don't need that. We don't need. What we need the results as it is, and then analysis of that, why it is so. Believe me, getting R square is equal to 1 or close to 1 is next to impossible when you use new and new chemicals. The biggest challenge in the chemical industry and all other industry where you use new and new products or make new and new product is the purity. Purity is the highest challenge. Where you buy polymer or where you buy any drug, where you buy any chemical, you see catalog, the purity is 0.99 price and 0.99 price and 0.95 price is a huge difference. Any industry, the most of the cost is at the last stage is purification, packaging, advertising, and distribution. Actual cost of the product is very, very less. I repeat, most of the cost is due to purity, packaging, and distribution. So keep this in mind. Purity step is very, very crucial. And since purity, you cannot make it 100%, you cannot get R square is equal to 1. Where chemicals or where the new products have been used. And this is where chemical analysis come into picture. It is not enough to tell that my compound is 99% pure. It is also required what is there in that 1% remaining. And that's where analytical techniques are essential. Today, we have reached to find out the impurity in ppb level or even ppt level, parts per billion and parts per trillion and beyond that. Today, people look for mercury content in a seawater in parts per billion or parts per trillion, where the science has grown. And this is essential to understand the purity of the compound. As I said, accurate knowledge of these thermophysical properties plays an important role in cost-effective design and operation of all these chemical and biochemical plants. Of course, the accuracy depends where you want to use and what is the reliability of the depending on. But if you want your product should go to the next level, I will come back to this topic again in after a couple of slides. We never synthesize, we never purchase our ionic liquid, even though many companies are selling BASF, Cytec, Ionic, Tokyo Chemical Company, or Sigma, Aldrich, Fluka, Merck. All of these are selling ionic liquid, but only conventional one and the popular one. We never purchase for 2 or 3 reasons. First one, if you purchase, it is expensive. If you synthesize in the laboratory, it is cheaper. Second one, purchasing as a limited catalog, limited number of choices. When you synthesize, you can design your own for particular property, particular application. The third one, when you make a new one, whatever you do with that is everything new. So the publication would be easy, so student can get some confidence and he can get a next job. So we are not a hardcore organic synthetic chemist, but we have synthesized more than 100 new ionic liquids and more than 50 the earlier developed by other people we have synthesized again. So in last decade, we have synthesized more than 150 ionic liquid. Synthesis is not difficult because it's either by acid-base neutralization or by metathesis or 1 step, 2 step, maximum 3 steps. We are not organic chemists. They who work on 15, 16, 17 or 20 step chemicals. And what is the thumb rule? When Lewis acidity of the cation and the Lewis basicity of the anion source both are low, your resulting salt will be 100% liquid. When both are high, it will be a salt. The only more chemistry or interactions you need to focus when it is a mix and match. So Synthesis was not very difficult part. These are the few, some of them without purification, some with purification. These are from different students, so the vials are different. And you see the chemist, organic chemist work in gram or milligram, biochemist work in microgram, organic chemist work in gram or milligram, physical chemist work in gram or 10 gram, but the engineer works in kilos. I had a collaboration with a mechanical engineer to work on vapor absorption refrigeration system. He told the smallest prototype vapor absorption refrigeration system I can make is with 5 kilo, but for you I can reduce it to 2.5 to 3 kilo. That is the smallest I can think. I said I usually synthesize 5 to 10 gram, but for you I can make 2-3 batch and make it to 20 gram to 30 gram or maximum 50 gram with 3 batches. So the need of engineer and the need of scientist is different. We need to understand each other's needs and their problems, then only collaboration will grow. So that's where collaborations are crucial, not only on paper collaboration, you have to mutually respect and then mutually understand the problem and then sit together and solve. So after synthesizing, the most important part was the characterization. If you don't have any side product, let's say you took compound A and B, you made a new compound C without any byproduct, but see that in that product C, you have any unreacted A and B is there or not, whether A and B is completely consumed or not. So this you have to check with various spectroscopic technique, NMR, IR, mass, and then mass will give you the molecular mass of all this thing, or GC, HPLC, trace amount of impurities. Please remember, if your starting compound itself has some impurity, definitely it will come into the product. And it is next to impossible to have 100% pure chemicals. And this is where analysis and analytical chemistry plays a crucial role to understand the tiny bit of everything. There is impurity, no problem. But we need to know what is that impurity and what is their implication. We need not to make so many efforts to make it our product 100% pure, but we need to make an effort to understand what is that impurity and what is these implications and the limitations. If you want to buy a polymer of what you call polydispersity, let's say polystyrene 1 kilo and the same catalog sigma Aldrich, if polydispersity index is 0.9, 0.95, 0.99 and 0.999, the price will go exponentially. Because to make a homogeneous part is expensive. Similarly, in other chemical also. So your starting compound, if you take very high pure, cost of the product will go very high. If you take little bit less pure, that impurity will come into the product. So how it will? So somebody was telling, if you see anybody cleaning their new car, new laptop screen or new mobile, cleaning, with the old cloth, with a dirty cloth, you must be in India. Sorry to say, our intention is good. You want to clean the screen, but you're using the dirty cloth. So the tiny particle or other dust particle will place on that which you can't see with the naked eye. Why I'm saying here, many organic people or many chemical industry or many chemists try to purify your final compound and make more and more steps and more solvents. Please remember, as you involve more and more steps and more chemicals, in addition to purifying your products, you are giving more and more scope to further impure. Because the impurity may arise from your new. The best one is to take the highest purity possible compounds, and the final one, no byproduct, complete product transfer. Then characterize it. So after characterizing, we study all these thermophysical properties. I think I spent too much time on this, but I think it's okay. That's was the sharing my knowledge. It's not only about my results. I already shared these slides with Neha madam and Amita madam. If you're really interested, these slides you can ask them, they will give you nothing is confidential, all are published results. So one more thing I want to touch and then I close. Apart from the purity and the characterization, the third one is accuracy. As I told you, I repeat, science is not about presenting the perfect results. Our results need not to be perfect online with the when you plot x versus y with all dots on the same line with the regression coefficient r square is equal to 0.999999 or 1. We don't want the perfection. Of course, while performing your experiment, you should be as perfect as possible. I'm talking about the results. Don't mollify or don't mollify or don't change, don't touch the data or don't cook the data. What is essential is in the genuinity and presenting with the compounds purity, the instruments detection limit and the accuracy. If you see all my instruments, I put accuracy there. Because the accuracy is a very, very essential part. And that tells you may have limitation of your detection limit or instrumental errors or compounds purity. When compound is not 100% pure, when your instrument has instrumental error, how you will get the 100% correct data? So present the data with the accuracy and the detection limit or the reproducibility, all these things, and the confidence level. By default, Microsoft Excel is a 68% confidence level or 95% confidence level. You understand while presenting the data. Data is future. Artificial intelligence and the data science and all these things are going to be future. And every field is required there. So the data, how accurate is to know is most essential. Otherwise, there is no, and the other thing is unit. So compounds purity, unit of your data, and the accuracy in your data. All these three are essential. Then you present whatever you got it. No need to alter it. There is no right and wrong in the research. Research is all about knowing the truth. If it is right, why it is right, how it is right, and if it is wrong, why it is wrong, how it is wrong. That's it. It's about truth. So you see here refractometer, density meter, ultrasonic velocity meter, viscometer, tensiometer, and conductivity meter, Carl Fisher titrator. This is the old one. We have the latest one also. It's a moisture analyzer. It's what you call coulometric titration. It will tell you in ppm level water content in your sample. Handling. Sample handling is the one of the crucial thing. And the research is not 9 to 5 job. You are measuring analytical balance. You should know the difference between analytical balance and the simple balance. You are trying to weigh sample milligram in analytical balance. On the table, you have a mobile phone with a vibrating tone and you are listening songs. Your table is vibrating and you are measuring the sample with milligram accuracy. No point. Or fan above your balance is running on the fifth. The temperature or airflow is circulation is not minimized. Then why to use the analytical balance of high accuracy? Spend a lot of money to purchase this balance. Balance can be purchased for few thousand rupees. Why to purchase in lakhs? You know this density meter, it's around 12 to 14 lakh rupees. And you know what is density? Mass by volume. If I want, this glass has a water, okay? If I want to measure density of water, I just take 10 ml of water by pipette, put it in a glass or a beaker, weigh it on the balance, 10 gram by 10 ml, 10 cancel, 1 gram per 1 ml. That's the density. I can do it in 10,000 rupees or 15,000 rupees. Why I should purchase 14 lakh rupees? It's all about accuracy. How accurate you can measure. If I ask you, can you calculate the density of water and tell me the accuracy? You took 10 ml in a pipette, you weigh in a balance 10 gram. The pipette accuracy is 0.1 ml and the balance accuracy is 0.1 gram. So on the numerator, you have 10 plus or minus 0.1. In denominator, you have 10 plus or minus 0.1. So 10, 10 cancel, density is 1 gram per ml. What about accuracy? Is 0.1 and 0.1 will cancel out? 0.1 accuracy in the numerator about gram and 0.1 accuracy in denominator about ml. Will 0.1 will cancel out? In Hindi movie dialogue we say, no, दुश्मन का दुश्मन दोस्त होता है. That will not work here. एरर पे एरर कैंसल नहीं होता है, एरर डबल होता है. I repeat, error पे error cancel नहीं होता. It's a propagation of error. It's not even double directly. There is a calculation you have to do. Error propagation. So you have to understand the compounds analysis, compounds accuracy, data, presenting data, data accuracy, and these are the crucial. When you write data, you don't know the significant digits. If I write 10, 10.0, 10.00, 10.000 has a different meaning. As a scientist and as an engineer, we should know these things. I will end my talk in 2 minutes. I'm overshooting the time. So I'm happy to present that we have contributed more than 7,500 data to the International Union of Pure and Applied Chemistry IUPAC database from IIT-Madras. It goes to all my students. And I will tell quickly one minute, one topic. This was I presented earlier, I think at Nirma. We took enhanced oil recovery. Here, the crucial thing is to understand the ionic liquid solubility by understanding the concentration through UV visible spectroscopy, through IR, and through NMR. How simple techniques can tell you about the accuracy and enhancing. And the enhancing was due to the small amount of ionic liquid attack the lone pair of asphaltene, and the asphaltene, which was responsible to hold, saturate, aromatic, and aliphatic, was released, and the remaining part was done by the solvent. It is not a pure solvent. The solvent was taken. This was the point. One was ionic liquid, one is a tank bottom sludge, and 100 is a solvent. So solvent play a crucial role. This is a perfect example how tiny amount of the ionic liquid can make wonders to get the 65% enhancement. One more thing is in enhanced oil recovery, how surface tension or the interfacial tension or the contact angle between the what you call hot water or the fumes or the steam and the crude oil and the rock, keeping everything as it is in the setup way, like polymer, salts, surfactants, everything, steam or water. We added tiny amount of ppm level of ionic liquid. The oil recovery increased from 52 to 72. That is 20% enhancement. And the responsibility is the only one property, surface tension. If surfactant kind of ionic liquid coming together with the oil and water interface, oil and rock interface we have not checked, by the way. That is also believed on the same principle. But oil and water interfacial tension can be reduced substantially from 30 to 50% by adding small amount of surfactant kind of ionic liquids. So how the surfactant plays a crucial role. Here, one more thing on metal ion extraction from the nuclear industry, from high level liquid waste, lanthanides and actinides can be extracted due to cation exchange, cation exchange, and the solvation mechanism. And this we showed threefold increase. So in all these three properties, we have used ionic liquid as an additive or extractant in a tiny amount. Not we can't replace the conventional toluene or dodecan, but the amount of the toluene and dodecan required is reduced substantially. The product has increased threefold. So it's a double dhamaka. As I told you earlier, sone pe suhaga. This side requirement of the organic solvent is reduced, other side product has been increased. like we say, no, energy saving is like energy production. You need not to you need not to develop the power and all these things. You save power consumption. You see in the classroom, nobody is sitting, fan and lights are on, you just stop. That itself you are saving energy. Saving energy is like a producing energy. So we have done also the solar vapor absorption refrigeration system. Here I told about my colleague from mechanical engineering. I forgot to tell. The earlier two examples were from petrochemical engineering department and ocean engineering department, and this was from the nuclear engineering department, and this one, the solar vapor, was in the mechanical engineering department, and the next one is chemical. Can you see that a chemist collaborated with the petrochemical engineer, ocean engineering, chemical engineer, mechanical engineering, metallurgy people, biochemistry people. So all are our collaboration. I didn't show my own strengths in the designing new ionic liquids and studying their thermophysical property. That I just quickly summarized. These are the applications with the different engine, and that's where the collaboration is crucial. When you want to go to the next level, you need to understand all level problems. No, I will contribute here only. I don't care what is happening next. Then people will not care about your results. So polarity. So far I talked about viscosity, surface tension, polarity, extraction capability, and refractive index. How refractive index is one of the crucial property in a pharmaceutical industry, and that is the key to develop highly pure compound. People says in the drug industry, when you have isomer cis and trans, cis may be life saving and trans might be life taking, and it's very difficult to differentiate other than refractive index. So refractive index, one of the crucial one. We have developed the correlation. We are the one of the first, I think, second group after Japanese group, Kohono group, to talk about this new class of compounds, the correlation between refractive index and the polarity. We also worked on the coolant terminal one, our engine fluids to cool the engines. We have succeeded in touching upon almost all properties except the viscosity. Very soon we will do. And dye-sensitized solar cell. Here, our ionic liquid, in addition to help as an electrolyte, it will also enhance this charge discharge and iodide to triiodide conversion, and during the daytime temperature expansion of the volume and consumption will minimize. So it's a multitasking. And we also worked on extraction of biomolecules. We have tried tryptophan, caffeine, and other compounds. So from bio waste to value added products. Here, phase transformation, solubility, hydrophobicity, and the charge density is a crucial, like what we have done Hofmeister series for the protein destabilization. Similar chiotropic and cosmotropic understanding, structure stability will help. In addition to polarity, we have extracted model amino acids, alkaloids, and phenolic compounds, and successful in designing, understanding the hydrotropic natures and recycling. So, and we also trying few more examples of desulfurization of model fuels and then diesel, carbon dioxide absorption, and electrolyte in supercapacitors and battery, ionogels for the sensing materials, and the pre-treatment of biomaterials or rice straw, wheat straw, just to start the hemicellulose or the initial compounds. And now the future is all PCBs, all our mobile phones, laptops, and all gadgets. PCBs are tremendous. Can we convert these PCBs or waste PCBs into extraction of these metallic fractions and not metallic fractions? So this our future. We are working on various things, infinite dilution activity coefficient and so on. This is the one I was talking about, Mark Shiflett. People generally go from academia to industry, but he served in industry DuPont for several years. Now he came to industry, one of the academia in Massachusetts University in the US. He collated, this is until last year, ionic liquids. So many applications have been gone in industry, pilot scale and commercial scale. He was telling more than double of this couldn't include because of the what do you call the patented or the restriction or the privacy. But future is ionic liquid has been touched various industry, mostly in Europe and US, and in India, Reliance is going to the next level. Used as auxiliary solvents, catalyst, electrolyte, lubricant, operating fluid, performing liquids, additive, solvent, all these things. But whatever you focus your next job or next research position or next abroad going for anything, please remember first you should like that position, then see that are you directly or indirectly focusing on government needs, society need, economic need, and touching the what you call sustainability. Is this research area directly or indirectly focusing on energy, water, food, and health? Because these are the needs for the future. And given the magnitude of this challenge, I am sure research conducted on this need definite thermodynamic understanding and physical chemistry understanding property, because that's where it will go from the laboratory scale to the R&D scale, to the pilot scale, to the industrial scale. And remember 3R policy: reduce, reuse, and recycle, which is extended into 7R policy. I'm not going into detail. And you have a better future with ionic liquid field as well, because millions of ionic liquid possible. The last one, my best ionic liquid for our students, those who can read, I put a color code also. It's nothing to do with the chemistry. It's a message: be positive, no negative. Thank you all, and you can write to me. My email